talk had unmanned systems in it, and when I realized I had 30 minutes, I couldn't get through it all. And since I am a material scientist, I thought, and I'm here for material science, I thought I would talk about material science as well. And it's very nice to follow the talk by Professor Matthias and Dr. Myers this morning, so I'm going to follow up perfectly on where they left, and also the talk by Professor Tarasan. So just to review briefly, hydrogen fuel cell, Debbie talked about this. So this is my view of it. We also build systems. And here she talked about the oxygen reduction reaction, which a lot of effort on the catalysis. And then there's this membrane called a PEM. You have things like bipolar plates, and we have the catalyst membranes. We're making water. And this is what a polarization curve looks like. So you're going to come down in voltage, and then it's not stiff like a battery curve, and it slopes like this. And there's three contributions to it. Activation, which is mainly oxygen reduction. Debbie talked about that. Ohmic, I can talk about that, but I'm not going to talk about that much today because for the purpose of time. What I'm mainly going to talk about is mass transport. And what I'm most interested in is performance at high power. And I also want you to think of a fuel cell. So what I'm most interested in is performance at high power. This is where you operate a fuel cell in here. This affects the efficiency and all sorts of things like this. And just for your cheat sheet, remember power equals current times voltage. So here's your voltage, here's your current. And we want to push this curve. Right now, current densities usually are up around 2 amps per square. Well, we want to be pushing this out as far as possible. If ever you see a fuel cell, this one's actually kind of a bad curve, but it's an old one. But usually I look for 1 amp per square at 0.6 volts, just as a starting line, to see if the data is good enough. What I wanted you to think about, though, is a fuel cell is really a water production machine. Everyone talks about bringing in hydrogen and oxygen, but it's making water. And you've got all this liquid water, it's gaseous water, it's liquid water, and you're basically trying to get that water out of the system. And again, people talk about bringing oxygen in and reacting it, but once you make this water, you got to get it out. So that's what I want you to think about today, is how do we get water out of this water production machine? A little bit more, why do we care about high power? So high power needed for propulsion. This is high power for high weight to volume. And if you can have a high power fuel cell, you can actually have a smaller fuel cell for the same power requirement. So a really, I see people say, well, I'm going to build a really cheap fuel cell that's really low power density. And you have this thing, the size of this lectern putting out 5 kilowatts. And you're like, I don't need that. And meanwhile, if you see the Toyota stacks and General Motors stacks, they're about this big and put out 80 kilowatts. So small is also cost savings. And not only for fuel cell automobiles, but also for flight. I recently watched Back to the Future. And this really was good. At one point, this was what came out in the 80s, and he shows this little they start off with a video camera, and they show this little thing that looks like a phone. They're taking a picture, and there it is. Here we are all walking around with our phones. That seemed so outrageous back in the 80s. But I watched the next one, and they had powered cars, and I'm like, oh, you cannot do that. There's not enough power to weight, so my engineer kicked off. And also, Harry and Ron in their flying cars. So where do we get the power for this? So we're very concerned about this. Hey, it could happen. I'm not going to give away my punchline. But so the presentation thesis, what I'm going to talk about is essentially, because I have this water production machine, the pores are really important. So I'm actually going to talk about the voids. So not the active material, but the empty spaces in this material become very important. So here, Debbie talked about a little bit more blow up here. So here's what's called the gas diffusion layer and the microporous layer. And these together form what's called the gas diffusion media. And I think that term was coined by you, Mark, was it, or no? It's one of your papers. It's common, yeah. Yeah, so the first paper I've read in it was one of his papers. So yeah, there's other, but we call it GDM. So I'm going to talk about this in the first part of the talk, and then I'm going to talk about the catalyst layers. This is what Debbie was talking about. She was talking about the individual catalysts. I'm going to talk about that structure it's going into. And this is platinum or porous carbon. And here's the membrane electrode assembly. I'm not really going to talk about that. All right, so we're ready to make our fuel cell. And here's all the abbreviations. And there is going to be a quiz. I'm not kidding. So I'm not a professor, but since I'm here at a university, I thought I would actually give a test. Okay, so here's all the different, and it's awful when this field, you've got gas diffusion media, gas diffusion layer, microporous layer, membrane electrode assembly, catalyst layer, catalyst coated membrane, PEM, platinum and carbon, Nafion ionomer. All right, we'll move through this. Okay, so we're in our lab, and we're going to make a small fuel cell to test. So typically, if you're making a real automotive one, you have these sort of squishy gaskets. But in our lab, we use a hard gasket, something like Teflon. And you put it between the two bipolar plates, your current collectors, and you're going to smush it. Got it? This is really important. There's a huge amount of science in this step. Because you could see that these are starting to get squished. And now how am I going to get water out of my water production machine now that I've squished all these pores? So here is a measurement, and in mils, you have to use the old empirical unit. And so you take the thickness of your gasket and you measure it. You use this little formula, this converts to inches. And we found, I'm just going to skip this part, but so you use this little formula, and we went through and calculated how I've got these commercial membranes. These are probably from W.L. Gore. I can't remember. It's in the paper. This paper here. And we're going to take just membranes and squish them between carbon paper. Look at this. So 0% down here. The best is 14% here. 14% compression, and that's based on that formula with the Teflon gasket. This here is an oxygen, and you can see 25% compression works better, maybe because you have more oxygen getting in, so you need, you can compress the pores more and take away some of that space for that oxygen to get in it. So this MEA compression at 14% significantly improves the performance in air, the worst performance at no pressure, and then overcompression, and 25% better. And this is for the SGL gas diffusion media. And I said there's going to be a quiz. So, all right, so we go in the SEM. We're like, this is great. And we look at the microporous layer. And you can see here at 25%, see how it's getting just squished? You're like, we'll never get water in and out. There's also Teflon in it, so it's hydrophobic. It's more complicated than just the pore structure. But you could just visually say, all right, we're done. So compression over 14% induces pore collapse. So that's good. So we sort of, at this point, this was 2016, and industry knows all this, it's just not really published. We also have to worry about interfacial contact. When you push everything together, you have resistance. Here, when you don't really compress it, you have poor interfacial contact, high resistance, low performance. When you squish it, when you compress it properly, all these properties are optimized. And if you over-compress it, you damage the microporous layer and low performance. What's frustrating in the academic field is no one tells you their compression, which thinks, do they not know? Or is it, it's really frustrating. So anyway, saga. Okay, my pet peeve. So along came Irina Zeniak, who's this very amazing person, called me one day and she said, I want to work in your lab for the summer. I'm like, okay. So she came and showed up like a ball of energy. And she actually had this data already. We were working with her on various things, but she said, I have this data I've collected at Stanford on gas diffusion media, and will you guys take a look at it? So we looked at her gas diffusion media, and these are here's the compression here, 0, 34, 41. So this is not what we were doing in the lab, but the data was already 6 months old, so we were like, we'll match the fuel cell data to it's easier to measure fuel cell data than go back to the synchrotron. So this is the SGL, and this is called wet-laid gas diffusion media, SGL 29BC. So it's not that picture of the nice microporous layer in the gas diffusion media. It's kind of a mess here. Look, it's all mixed up together. Here's the gas diffusion layer, and here's the microporous layer, and they're actually all squished together. And you can see that as you compress, they all just kind of get squished together more. When you look at dry-laid gas diffusion media, this is from a company called Freudenberg. Look at how nice that actually is like the picture. It's a nice microporous layer, and then this nice layered carbon structure on top. And as you compress, there's really no impact of changing these pore structures. So look at the performance. So if you want to actually, if you want to impress your program sponsors at DOE, switch from SGL gas diffusion media to Freudenberg, and overnight you get a 20% increase in performance. So look at that. Just the two different gas diffusion media in my region of interest out here at 0.6 volts. See how the power just increased. This is the resistance here on this side, and you can see the resistance of the SGL is a little higher. Now I'm going to talk a little bit more about the conditions. What humidity is this? It's 100% RH. That's not really a realistic condition. I'll talk about that in a little bit. So if you look at the current density, look at the increase here, just from switching out basically a passive layer of carbon. You know, here these catalyst people are doing these heroic measures, going to synchrotrons, and we just put in a piece of paper. And it looks like, I wish I'd brought a piece of it looks like basically black construction paper. So, and here's the difference in resistance. So what's happening is we compress. So here's, when you look at the computed tomography, the SGL has very, very cracked microporous layer. And they basically just, the cracks disappear. So now you're losing that gateway for oxygen and water. And here's what the microcracks looked at. And Irina showed that, again, our region of interest is more in this here, but she had the data already, so we went with it. And you can kind of fill in the gaps. But look at how the compression, you lost most of the cracks as you compressed. And the thickness of the microporous layer decreased. So the microcracks are lost in the microporous layer with increase in compression, and then they decrease the availability for oxygen and hydrogen transport. And look at this Freudenberg dry lay GDM. I mean, there's just no, it looks identical with compression, so it's just completely robust to this process, and so you're not blocking your pathways. Pore size analysis, again, sort of reiterating, here's the voids. So the voids, even though they're empty, are actually doing a lot of work. And I meant to say at the beginning, this is very relevant to battery work as well, because they're compressed and you're trying to get lithium in and out and transport and electrolyte and things like that. So this is very relevant to all electrochemical systems and electrolyzers. So look how the void here in the SGL is squished and goes away. And it's really, we're just able to retain that void structure better in the SGL. And see here, this is the SGL, how it's bimodal pore size on the bottom. And again, the pore structure doesn't change, so it's very interesting. But to make things more complicated, so if you're at a fuel cell company or you're trying to actually make a car, you have to worry about durability. I don't know how durable the Freudenberg GDM is. I don't know. Startup conditions, you have to start from minus 20 degrees C. So there's all sorts of other parameters. And here, this is a really small, this is all published. But you can look at, and unfortunately these are on different axes, but the condition, it also changes depending on the R8, the relative humidity and temperature. So we've got 40%, 100% RH, 80%, 100%, 80 degrees, sorry, 100 RH, and 80 degrees, 25 RH. So the compression also varies on your condition. You could almost imagine, I don't know, I've heard this talked about, but you could almost imagine that if you were really built a slick fuel cell, you might even want to change the compression on the fuel cell for different operating conditions. And you know, that's possible. I don't know if it's done. I don't know. That seems logical to us that you might want to have a variable compression system, perhaps different conditions for startup or dry conditions. Okay, here's your quiz. Oh, it went. Wasn't supposed to do that. All right. What is gas diffusion? Oh no! It's paging. All right, it was supposed to go through. So here it was. What does GDM stand for? Gas diffusion media. Which GDM gives higher power performance? It's the Freudenberg. And how does the compression affect the catalyst layer? You're supposed to be scratching your head saying, I don't know. And the question is, I haven't told you that yet. So you don't know. So you're saying, all right, you're compressing that, and you know, Debbie's trying to get oxygen in and out and water in and out of her catalyst layer. So how does this squishing process affect that? Why is it animated? Oh, it turns out, okay, so we build fuel cells in our lab, and we built our own spray process. And this is all published, so anyone in academia who wants to build their own ultrasonic spray process, the spray nozzle costs about $6,000, and then we just put it on a router, and a CNC router, which costs about $2,000. So we built up our own system for about $10,000, and we write our own code in G code, and it's all published because we're trying to give this away. We looked at you guys all have these commercial systems, but they're like $60,000 or $80,000, and it would take us a really long time to buy that. So one of our engineers said, oh, I know how to build that, and we built it. And it's really nice, and it's a very flexible system. So this is all published in Analytical Chemistry, how to do all this. So we're building our own fuel cell electrodes, and Yannick, he's co-author on this, and Yannick really, he's the brains behind this catalyst-coated membrane stuff, and actually the compression stuff too. He's reading the literature, and he said, you know, I see a lot of people looking at this short side chain ionomer, And then there's the Nafion long chain ionomer. You say, well, where is that? Well, in the catalyst ink, and Debbie didn't really talk about this, you've got carbon and platinum, and then there's sort of this Nafion or ionomer squished in there. So we're going to add one of these into the catalyst ink when we spray, make our catalyst layer, and then we're going to put together the system with the Freudenberg electrode, put it in the cell and test it. So really, you know, you could say there's a huge difference in performance. I should skip ahead. Hold on a second. Oh, I don't have the pole curves. It turns out, I have them on the next slide, but it turns out when you change the ionomer, and we're not sure if this is chemical or just serendipity, you really change the pore structure of the carbon. So you have one type of carbon with little micropores in it, and depending on the ionomer you add, it changes the pore structure. Now this is just with BET. So before we were running to the synchrotron, we were doing computed tomography, and one of the women in our group said, I'm going to go do BET. I'm like, well, that is never going to work. Well, it works pretty well, and it's cheap, and most chemistry departments have one. But look at what a difference it is. It's changing here more pores in this very small pore region for the equivion, and fewer up here. And there's a professor in Canada, Eicherling, and he's done a lot of work on pore structure. There's a group of thought saying it's all oxygen resistance affecting the electrodes, and Eicherling says it's all the pore structures. The primary pores of the carbon support in the catalyst layer containing the SSE equivion ion are more hydrophobic, which is expected to improve reactant transport and water removal. So, and we see with this approach, we were able to we bought a commercial catalyst, platinum cobalt, and we mixed it with the equivion ionomer and put it with the Freudenberg electrode, and we were able to meet, this is very low platinum loading, and we did this in our lab, just about able to meet the DOE targets. Here we are in black here. Hold on a sec. Oh, here on this side, this is 65% RH, so we're not quite, these are two different NRL electrodes. We're not quite at full power, but look at this beautiful performance. We're at 2 amps per square at 0.6 volts. And that's with a very, very small platinum loading. And the key was that equivion ionomer and the right gas diffusion media and compression. So not really intuitive when you start off, you're thinking catalyst, 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 but it's all this other stuff wrapped around it, which is so important. And we're not chasing the DOE goals. That's not our goal at all. So Yannick comes up, he says, I want to start making graded electrodes. I'm like, okay. So, so we use that nice spray printer we have, that nice sort of spray. It's very, because we own it, we can program it however we want. So we start a conventional membrane electrode assembly. He's going to add on layers at the cathode and anode, and then build it up. And what he wanted to do was, we're calling it additive manufacturing. That's sort of a buzzword, but just grade the catalyst layer. So is higher microporosity throughout the electrode, all equivion site short chain, always favored? Is it better to grade the microporosity towards or away from the membrane? And which electrode structure maximizes power? So that's what we went into looking at. So Yannick went in and he was just looking at 8 layers and a pretty medium loading of platinum. We don't really try to reduce platinum, we're just looking at high power. So he looked at different sublayers and he changed the different types of carbon and porosity just by changing out the materials and trying these different ways. And it makes a really big difference. And again, this is no materials invention. This is just mixing them up differently. So these are TKE catalysts. Which one did he use? So he had this was with different types of equivion and Nafion. Remember I said adding in the different ionomer changed the porosity. So he went through and changed the different layers, 2 layers with equivion, 2 with Nafion, and he went through and I mean, it's quite significant performance. If you look out here, again, I'm going to draw your eye to 0.6 volts, how he's able to, with the graded electrodes, 4 layers of equivion, 6 layers of equivion, really outperform just the TKK equivion standard. Isn't that amazing? Just by changing the porosity. And then someone said, hey, why are we using same gas diffusion media on the cathode and anode? That seems like kind of a stupid idea. So got in the lab and tried different mixtures of Freudenberg gas diffusion media. And look, here you go. Jumps out again. And sometimes we're below 2 milliamps per square, and sometimes this depends on the condition. This is at 25% RH. One of my big ideas I have, like every 6 months, is getting rid of the humidifier to save a lot of cost in a fuel cell. So, but isn't this amazing that, again, at this very low relative humidity, look at how far we just increased the performance just by changing out that paper layer and the type of paper we used. So we're doing okay. So my conclusion is porosity is really important. The compression of the gas diffusion media has a very large impact on the performance at 0.6 volts. It affects the water management through changes in pore sizes, and the design of the gas diffusion media has a profound effect. The control of the porosity in the catalyst layers is also really important. Control through selection of the ionomer, the fabrication process, and mixtures of porous catalysts. And some simple methods such as BET can be used to make a lot of progress. You don't necessarily have to run to a beam line. And new methods such as computed tomography certainly are also very useful. This is at you guys know what AUVSI is? Association from Unmanned Vehicles Society International. So this was at AUVSI a couple weeks ago. This is a Bell helicopter. They're building it for Uber. This is actually not unmanned, but it's a 7-seater, and it's an octocopter. So it's gonna, you can look it up online. It's super cool. Like, so they had it, everyone just walked up and was smiling because it was so freaking cool. Now, the secret though is, remember, you know all these little drones that have come out recently? All that's due to electric power because you have to control the rotors. It's very hard to control propulsion accurately with turbines. So this is on a gas turbine. Of course, I'm asking them, like, how many horsepower do you have? So it's on a diesel turbine, which, you know, tremendous horsepower. It's, you know, tremendous horsepower. But you really can't control these 6 different turbines that well without electric power. So you could make electric power from a turbine, you know, from a generator, but now we're looking at a fuel cell or a battery. First you'll do a battery vehicle, but this is hopefully what's coming, our flying vehicles. That's it. We have a whole bunch of papers. You could just go into Google Scholar and look up my name. And we had tremendous help from our postdoc. Rob Atkinson did a lot of this work, Megan Sasson, Benjamin Gould, and Chris Netwall. Okay, thanks.
We have time for a few questions.
Yeah.
Do you have a sense for that using the porosity makes a big difference, but you have a sense for like what those boundary conditions are?
No, I mean that's a good question. To some degree, I mean we're not doing materials invention. We're buying materials. We don't know who. Some OEM worked with Freudenberg to develop this gas diffusion media, and we don't know why. We're just able to buy it. So we're trying to optimize it and then also publish it for the general benefit. But I think it also depends. It depends. So we only look at 80 degrees C. We look at 40 degrees C in different relative humidity. So if like I can't say which gas diffusion is better for startup or things like that. So I think you'd have to get in and look at it. But I think the point is that it'd be nice for people when they talk about their membrane assemblies to at least report the gas diffusion media, the compression, and you know, take a look in your own lab. Because it's not that, I mean, it's an arduous process. You got to work through it. It's expensive, all the materials, but you can't get the right performance out of your fuel cell until you have the right gas diffusion media and the right compression. Yeah.
Have you looked at uncompression? Does the mechanism work when you just variably uncompress?
Uncompressed, well, we did look at no compression.
But once you've compressed, uncompressing.
Oh, they kind of,
Do you squish?
there's a little bit of relaxation. The first thing you want to do is make good physical contact for the electrical conduction. So you want to form that, and I think you can relax it and do okay.
That's your idea for
variable compression. Yeah.
Okay. But you haven't looked at that yet.
We haven't looked at it. I'm sure someone's looked at it. It's not published, but I mean, it kind of just raises your. I mean, if you think of it, it's sort of as an accordion. I don't know. I think it's I think it's very interesting. And maybe that's something also, maybe from a material science perspective, is maybe look at gas diffusion media or battery materials that can change porosity with compression, and then you could start to have a more dynamic situation, even for a battery, right? If you can change the porosity of a battery, if it's cold, if you're charging, maybe you want different porosity during charging conditions than discharging conditions. And so maybe this is a material science challenge of how to develop this porous media that's reversible, and you can form good contact.
There's no further question.